Hello, good afternoon. Let's start our class. We have several questions submitted up to now, and I would like to answer all of them. I would like to ask from the questions of people who are present here. I see the first one is Artur. I would like to see to understand your question better. Looks like you have error, 5% error on small angle of attack, but on bigger angle of attack you have 15% error. So you would like to
Isso.
know if this error is because of viscosity or another reason, right? High error is caused by two reasons. First is that you have no viscosity, so it's basically calculating with schematic viscosity, which is very different from the real viscosity. There is so-called approximation or numerical viscosity, and this is not inside the model. So there is no model of turbulence and there is no model of the boundary layer. So it's basically just flow without viscosity. When you start to have a stall condition, the main reason of the flow separation is the boundary layer and viscous interactions with the flow. And since you do not have a well-calculated viscosity or correctly calculated viscosity and correctly calculated boundary layer, of course, this error grows. The error grows. And it's normal. I already explained to you that don't worry. In work 2, you can have this error growing. But in the work 3, you will see if everything is correct, you will see that the error must be smaller, must be reasonable, right? Also possible to have big error also in work 3. This happens in case if your body is not compatible with the chosen turbulence model. For example, the mechanism of the vortex separation is in real airfoil is very different from the simulated. This can happen because what we are simulating, for example, K epsilon or K omega model, they are all based on averaged uh, equations of Navier-Stokes. And it means that we do not see the oscillation, we do not see the perturbations of the flow, and all perturbations, they come into the equation as its average values. So we cannot see a transient picture. And also another reason is that inside K epsilon K omega model, we have so-called characteristic length, which is calculated as a distance from the wall to the body, but not always this distance can be calculated. For example, when the boundary layer is separating, is growing in a different way than it's uh, uh, going together with the wall. And in case of separated boundary layer, it does not work, this definition of characteristic distance from the wall, and it breaks completely the turbulence model. And in this case, we can also observe high error, but not always it happens. In several cases, in some cases, it will not be visible. So it depends from one case to another, from one airfoil to another. So we can expect probably better situation when you calculate the viscous flow, right? Because of correct calculation of the viscosity and the boundary layer. But also cannot happen if this turbulence model will not be compatible with the type of the flow you have around your airfoil. Depends on many factors, so we cannot say definitively before simulation how it will be. Okay, but since the airfoil is a streamlined body, when the flow is going smoothly around the wall, we expect that K omega or K epsilon model are suitable for this kind of problem, and they will result in a much better precision.
Você mostrou lá no vídeo do YouTube que para a gente fazer a simulação para um perfil de 10 centímetros, né?
Yeah,
0,1 metro.
but you know why it was 10 centimeters, to keep the same Reynolds number as I have in experiment, right?
só. Mas é por... naquele gráfico que a gente tem experimental é para 10 centímetros?
Not, I adapted as I already showed in the previous video. I can give you the link to the previous video where I show how you calculate the size of the airfoil to correspond to experimental data in terms of the Reynolds number. So we have the same Reynolds number in experiment and in the simulation. But to have same simulation Reynolds number, you can change only two parameters. Or you change velocity, which is difficult because you can come to compressible flow, and we don't want to calculate inside compressible flow. And the other possibility is to change size of the body, the Horn value. So it's quite safe, and just adapting the Horn, I can calculate the same Reynolds number as my experimental data.
Certo. Era até essa questão do Reynolds que eu também fiquei um pouco na dúvida.
Yeah, I already explained before. Please.
Então, tá ok. É porque até eu fiz quando eu joguei no Xfoil, para comparar os gráficos de CP, né? Eu tive que dar uma roubadinha lá nos valores para caber em 0,1, porque na minha simulação foi de 0,1 metro, né? Aí eu dei uma roubadinha lá e deu certinho, tipo, encaixou tudo certo, tudo até mostrou, até eu consegui ver um pequeno erro, né, comparando tipo, do Xfoil com o do Ansys. Tá, eu acho que era isso. E outra coisa, você pede pra gente colocar o Convergence plots, que são os residual plots. Coloca também para cada ângulo? Tá.
Could be nice, could be nice. Or for small angles, it's practically same. And for the stall condition, it will be different because the flow separation starts to happen. But if you can put for every simulation, there are only 5 cases, and you can put 5 small plots. It's nice to observe the convergence, because every time starting from 0 to increasing angle of attack, you have more and more and more steps to converge. And then it will not converge, definitely, when the angle is too high.
It's just
okay. It's just for you to understand the idea of the convergence and residuals. Okay, you are welcome. Let's go to the next question of Aleph. You could not save, right? You could not save the text file when the flow is not converging. At least you could not find. I've already prepared the simulation for this case, and I will share my screen to show you how I define the text file or reports, and I already checked they are generated during the solution, so every time step they are updating.
Ainda voltando um pouco naquela questão do tamanho do perfil que a gente analisou. Uma coisa que eu notei que foi que o Reynolds desse para esse de 0.1, o meu deu 9, porque o meu work one eu trabalhei com um Reynolds de 9 milhões. E aí para esse eu achei um Reynolds de 900 mil, né? Porque como é uma casa decimal a menos. Mas é isso, tipo, as coisas bateram. Aí isso tá tudo bem, né? As coisas seguem. Porque os valores deram muito certos, tipo,
If you remember, the lift coefficient is practically independent on the Reynolds number. What will be important is the drag coefficient. When you start to calculate the viscous flow, it's very sensitive on a Reynolds number. The viscosity and the drag as the main source has main source of viscosity is influencing. Okay, so the lift is basically not sensitive to Reynolds number. You can see that it's the same for all cases. So I already have found this. I shared my screen of Fluent with you, and it's quite simple. I created here on the left side 2 report definitions. Okay, these 2 report definitions, I think you know how to create. It's just put new and is the type, right? It's just the force in a certain direction. Okay, let's try to. edit. For example, this is how was created. The axial force coefficient is projection on x coordinate, right, of my wall of the airfoil, and force vector is 1 because it's vertical. Okay, so not vertical, horizontal, sorry, horizontal. So when I needed to make a report of text file, for example, I already created here report file. You can just click again to create this report file. You just click here, report file definition, and then you have a list on the left side what you have, and on the right side what will be inside your report file. I already added because I need both axial and normal force coefficient inside my report. And then I write a file name. It will be cout, or it's a coefficient output. Right? Coefficient output and txt text file. I click OK and get data every one iteration. You can, for example, if you want more points, you put smaller value of iterations, for example, one iteration. If you need a very few points, like every 10 iterations, you put 10 here, right? Also, when you are calculating with the time step, like a transient flow, it will appear here time step, or can be one iteration, or every time step, or every several time steps. Okay, so get data every one iteration, sorry. And then print to console is will be printed here below. But I don't want to print. I don't want to see these parameters in my console. I just want to save as a text file. And every iteration, it updates the text file. Okay. And I also have the same. Just a moment. I will go back to my report definition. Report plot. Report plot is how will be plotted on this graphical window. This is my report plot, so I can see. I already prepared the high value of the angle of attack, and you can see that is oscillating. It will not oscillate with the good one frequency, right? Since it's a non-linear process, probably there are several parameters influence on this process of, not process, a parameter of normal and axial force coefficient. So it's composed by many, let's say, frequencies. But we can determine some behavior. At least we can see two periods here. And by this curvature, we already can see that is repeating the normal force coefficient. So somewhere in the middle, I stop my calculation and I get my flow picture. And this data which I have here is automatically saved in my text file. Here is the path. It's in my disk C, okay, airfoil, and then you see exactly where it is. If you put already the text file name, by this text file name, you can find easily where it's saved. It's always saving inside the project where you have your all simulation files. Since you are calculating inside Fluent, it will be inside the folder Fluent. Okay, and then your text file is there. You can create as many text files as you need of different parameters. In this particular case, I put two parameters on the same file, axial and normal force coefficient. On the same file. I can put them in different files, for example. It's also possible. But I think it's easier if you have all in one file. I would like to know, Aleph, if this is what you wanted to see, or you had another problem which I did not explain yet.
Well, when I created the report definitions, there was a checkbox, and I just clicked to, if you click new and put a new force definition, there will be a checkbox.
Okay, this?
For already creating the report file.
Okay, let's see. Let's see. For example, I create a force report of the drag. I will see my wall, right, and
Yes.
create a
There is
report
report
file.
as well.
Okay, you can
Yeah,
do it, and somewhere you must. Okay, I will click on CA, right? CA2, for example, and I click OK. This my CA2 is here, and but is nothing is just a moment. Okay, CA2R file, I can edit here, and I can change also the parameters. Only CA2 is selected, but you know what I'm trying to do is to change at least the extension to TXT, so you can easily open with your notepad. You don't need to redefine the out extension. So like this, and you
the
can
problem
also
I have
change. And it saves.
when
It saves. I
you
click OK, close. I start to calculate. Just a moment. I will see now. I start to calculate from this point. It calculates. It plots the. It calculates the iterations, and I will just open my Explorer, and I will see where's the file. Yeah, I see this TXT file. I shared it with you just a Fluent window, but I already found in my Explorer the file is being created on every step. New values are being saved. So it's working. In this way, 100% is working. Maybe it was not saving because probably you put other number of iterations or very high value of number of iterations. Just
it was a very high value.
Just take a look. Just a moment. I will go back to my report definition and just take a look how many. You see, I click so many times and then only after my report appears. And maybe you put very big value here. Just take a look. And should be
Yeah,
iteration, not time step. And
I think I didn't change that part. I don't know how it actually
let's do the following.
but
If nothing is working, as I suggest, you can send me the project. I will take a look and I will see what's the problem. Because it's very, very
okay.
simple and very fast to check. It's absolutely no problem
It's
for me
just
to
that
receive and to see again.
I it's just that the ones that converged, all the files appeared in progress files, DP0. Ansys created the folders, and all of them appeared as the format with the name I gave, and all of the ones that converged. For some reason, the ones that didn't converge did not show the report.
That's strange because it saves new parameter every time step. It does not save at the end. It saves every time step. So maybe you put something wrong in this simulation. Something of strange.
Yes, there is a very big difference. I think I didn't put animations in some of them, and the folder has doesn't have as many parameters inside. But all the ones that converged have the txt with the ca airfile.out and
Yeah, I
airfile.out.
understood. I never saw that report is not generated without reason. You know, this should be the reason. So if you cannot solve by yourself, send me and I will take a look, and it's easy to solve. Okay. So
I
what?
can I can screen share the folder just to see how it is showing some and not others.
Do you want to see the folder?
Yeah, I
Okay.
can show it here.
Okay. Okay.
So there are the files, and the saved files go either here or here. And here, if you go to one of them, there are a lot of parameters related to the
Yeah, every
animations.
FLU is you even save every time step. It's so much of spending time, or sorry, space, waste of space. But okay.
Yeah.
animations.
And it generated the files and this FFF things too, and some other TXTs. But in the cases that didn't converge, like this one, it doesn't really have the TXT with the CA.out or the CNR file.out. I could only generate the images.
Probably
I
it
can
was
see that
saved
it
in the
doesn't
other
really
folder.
converge.
Try to take
Yeah,
a look in the other folder.
Yeah, I looked at this default global.
No, it
Since
should be in the
images
Fluent,
event.
but maybe you not intentionally changed to another folder.
Yeah, I think I didn't change anything in the parameters. I have had kind of a hard time looking for the images because I was looking here instead of in the other DP0 because there are two folders with
I
them,
got it.
but they aren't here too.
What I recommend if you are simulating, do not save on the disk these animation files unless you don't want to make animation later, because they consume so much memory on the disk. I recommend you, instead of choosing the disk, choose the memory. So all these frames will be saved inside memory, and it consumes very little of operational memory. Usually it's enough to, if you would like to create some video or some animation, it's enough and much better. Okay. And you can easily delete all animation files when you do not need them anymore. You just delete all these animation files, and Fluent will not have any problem to load.
Okay.
So when you don't need these
Then
files, just remove, because they occupy a lot of space and they usually create a lot of problem when you transfer project from one space to another. It becomes very difficult because of the size, of the total size.
Can we include the animation files somehow in the
Of course.
report?
No, in the report there is no sense, because we are simulating stationary flows. What kind of animation you are expecting? Animation is good when you are simulating the transient solution, the transient flow. Then animation is very interesting. If you will try to do animation for a stationary solution, you are not animating progress of the flow in time. You are just calculating progress of solution. From mathematical point of view, it's interesting, but it has now no absolutely relation to a physical changes in the flow which happens from one iteration to another. It's absolutely useless from the physical point of view. It has only interest from the mathematical point of view. But in case of transient, is the physics you are simulating from one time step to another, and then creation of animation is interesting.
Are we supposed to show animations for work 3?
No, I don't. I did not ask to have any kind of animation in work 3. Don't show. It's just for yourself. If you would like to make some kind of animation, just keep it for yourself. Okay?
It's just because in GinaFlu, we do the works in GitHub, and there is the option to put GIFs.
Great.
In the project.
Great.
And I remember doing some of that and thought it would be interesting, but I see that LaTeX has no option of including GIFs.
No, because LaTeX is creating PDF, and how you can add video to PDF.
PDF doesn't work with GIFs.
It's nice when you're making some presentation, but again, on presentation must be presented something of realistic, right? When we are calculating transient problem. When we are calculating change of stationary problem is not realistic, and better not to show. Okay, I hope this was clear. If you have other problems, just send me a private message and the project, and I will take a look what can be the problem of generation of this text file. 2 questions. In one simulation, continuity residual converged, but the velocity one still decreased, but have already reached 10 minus 6. can we say that calculation is complete since the residual is really small? I already answered this question today in the Moodle, but I can say you that I confirm that we usually consider flow converged when the residual is smaller than 10 minus 4. Okay, 10 minus 4, it means that from one step to another step, you have a change of parameter smaller than 1/10 of percent or 1/100 of percent, sorry. And it's an infinitely small value of changes, and we consider that change do not happen anymore. So 10 minus 4 is already considered as converged. For some simulations, you can decrease this value if your simulation is converging really, really slowly and you need more confidence on that convergence happen, then you decrease it to 10 minus 5, 10 minus 6. For slowly converged processes, for example, when you are simulating together heat transfer, for example, and the flow, which has very different characteristic time, or for example, flow and chemical reactions that have very, very different time scale. Then one process looks like it already converged, but the other process is still not converged. In this case, for one process, we put a bigger value of residuals. For another, we put smaller value of residuals. Just a moment, I will share my screen again, and I will show you where exactly we set, if you did not find yet, where exactly you set this value of convergence. Okay, the Fluent is here, and let's see, the monitors, residual, and all the parameters we have here. Usually, when you are calculating with viscous flow, Fluent is automatically setting this energy convergence of the energy equation to 10 minus 6. But it's a very, very small value. Usually, we can put 10 minus 4 or even 10 minus 3 as for other parameters, and already can be considered as convergent. For different types of simulation, convergence happens faster for some parameters and slower for the other parameters. Usually for the viscous models, convergence of the turbulence model is happening faster, so you can observe much smaller values of residuals for the turbulence model parameters than for the energy and velocity components. Okay. Here we cannot observe the difference between continuity and energy equation because it's basically the same solution. We just have an energy equation because energy source is coming from the viscous model. But mathematically, it has no difference with respect to the continuity equation. Okay, this was answer to one question, and the other question was that the drag coefficient in work 2 is not important as the lift coefficient, and I confirm that is true because in work 2 we calculate only non-viscous flow where the lift coefficient is calculated precisely because it's is not so much dependent on the viscous forces as the drag coefficient. Where in work 3 already calculation of drag coefficient is very important because the viscous effects form the main source of the drag. Yes, your guess was correct.
I just want to add something about the residuals. If the residuals is, I would say, around 10 power minus 2, but it's still constant, it stays constant, is it good or is it even if it's or not?
Like, for example, in case of my simulation, which I show now, right?
Yeah, for example, it stays constant?
Yes, it's not so much constant, but more or less, yeah.
Higher.
I saw many times that there are several reasons when the residual can stay even a constant, practically constant value, straight line, horizontal line, but it will not go down. it means that somewhere in your simulation there is a provocation of the flow changes and probably flow oscillations. And these flow oscillations, they are constant, and there is a source and there is a reason of this. Some kind of reason in this simulation which I show is that always we have formation of new vortex in the flow. A new vortex in the flow, and then dissipation of the vortex, formation of a new vortex, and set. Also, transformation of the flow always happening. In the other simulations, for example, simulation of the compressible flow, provocation of such picture can be a model transition from differential equation to algebraic equation system when the shock wave in compressible flow cannot be calculated precisely, and it's always calculated approximately. So because of this transformation transition, the velocity changes quite fast, quite rapidly, and it crosses Mach 1. It from one side has supersonic velocity, from another side has subsonic velocity, and because of this flow transition from supersonic to subsonic, the type of the equation is changing from hyperbolic equation to, I think, elliptic equation. I think it's elliptic equation, if I'm not wrong. And because of change of the type of the differential equation, the method of solution is completely different. And so the program is switching from one method of solution to another method of solution, from one step to another step, and back, going one method, another method, then returns back to the first method. There is a specific point where it happens on this shockwave transition, and it, from computational point of view, generates small perturbations. But these small perturbations, they basically do not influence on formation of the flow and flow characteristics, but always this kind of oscillation keeps constant on a quite high value, like 10 minus 2, the residuals, so they will never drop. So they cannot drop because of two reasons. First is some physical process that is happening, like in case of the airfoil, or the mathematical transformation, which is changing the nature of the differential equations. And this mathematical oscillation is happening. So can be physical, can be pure mathematical problem. Okay, but every case is different. We need to see what is the source, where happened this kind of oscillation. It can be seen analyzing two different time steps, pictures from two different time steps, so you can get the residuals distribution in space, and you will see where it is generated. And then we can say if it's important or not important in flow convergence, or if it can be considered as converged flow, or it cannot be considered as converged flow. There are many different cases. Okay, when it's physical, it's not converged. When it's mathematical, probably it's converged, but from the mathematical point of view, it's changing on every step because method of solution is changing on every step. Okay.
Okay, thank you.
Okay, you're welcome. I would like to go to the fourth question. We have a pressure distribution that have the same shape, right? Same shape as the distribution from experimental data. Probably you say about the pressure coefficient, right? And but the values are a bit bigger, probably it's the absence of the viscosity. Maybe it can be the absence of the viscosity because viscosity will consume some part of the energy. So for the pressure will be smaller values because of, okay, the energy, the total energy is the same. If we take some part for the viscous energy, then for the pressure will be smaller values, and will be smaller values of the pressure coefficient. Absolute values of the pressure coefficient will be smaller. Also, because of the Reynolds number different in the simulation and experimental. I don't know. Can be this reason or not. Probably for work 2, the Reynolds number is not so much important, right? Does not have so much influence. It depends how different is really, how much different. If we are talking about a difference of maybe 5%, then the viscosity can solve the problem. If we are talking about like 20-30% different pressure, viscosity will not consume so much energy, and pressure will not drop 20-30%. Okay. So let me know how much is the pressure difference.
I'd say it has about 30% difference. It's pretty big.
Yes.
I'd say
30% is too much, and by viscosity, it will be not possible to compensate. So need to search where is the error in the simulation. Need to search. The source can be different. The source can be the boundary condition, wrong boundary condition. The Reynolds number, it's basically will not influence, but you can try to change. Okay, in the simulation, you have 1.5 million. In the experiment, you have 3.7, like 5 times or 4 times smaller. 4 times smaller in the experiment. So why not to reduce the velocity 4 times, and you will have absolutely same value of the Reynolds number in simulation and experiment. And try to see.
All right.
Okay.
Yeah.
Let's do the following again. If you have some real problem that you cannot solve, don't wait another week. Don't wait until you solve and or some miracle will happen. Usually it does not happen. Send me the project. I will just take a look really fast, and I will see at least from point of view of the boundary conditions or other model or other parameters is correct or not. Just not to wait. I usually, when I receive from students this kind of question, I answer really fast, and then you can proceed or continue looking for the problem.
Okay, that's nice.
Okay.
But yeah, I think all of this is really odd because I follow the video instructions pretty closely.
Okay. But you know, what I give in the video lectures, in these videos, is not the, how to say, solution for all possible cases. It's just one solution which I consider nice. Okay. There are many ways to solve the same task and to receive a good value, a good result. Something which I recommend you as the reference, but maybe you need to change something to receive better solution. And it should be quite clear that there is no universal solution for all cases. You know, aerodynamics is not working like this. You have a lot of experience, you receive a lot of experience simulating many different cases, many different geometries, many different types of the flow, and then you start to get experience. This is our goal. Okay. I suggest the following from the practical point of view. Since the time is not infinite, you need to solve as soon as possible. So if it's not solving fast, just ask. Maybe we have some call like outside of the class or inside the class, and we solve this problem.
Okay, that's nice. All right, then I'll follow your suggestion.
Okay.
I'll try changing this here and see if that changes anything.
Okay, nice. So these were all questions submitted for today. I would like to see if you have some other to ask now, and let me know here by voice or in the chat, and we can discuss.
I recalculated the error we did last time, dividing by the maximum value, and I think I'll have to change the conditions. Should I message you about what conditions should I change based on the error I found in the simulations?
Like which kind of condition do you mean?
Just the error, just to talk about that, I took angles of 0.2, 1.7, 3.2, 4.5, 5.9, just like the table in the article. And the error I found after the changes on CN is in percentage is 5.47 over 0.2.
Okay.
Then 11.22, 17.35, 21.66.
Yeah, okay, it can be bigger when you approach to stall condition. Just make a nice report.
I have 50% error on
50.
11 degrees, and I don't even I didn't even stall. I
see.
didn't yet to
No, the
calculate
50% is too much. Probably something is really wrong. Just send me the picture. I will just take a look. But probably you need to change something. Or check again the experimental data. Maybe sometimes people confuse experimental data from the airfoil and experimental data from the wing. Because the lift coefficient also exists for the complete wing. And it's very different from the lift coefficient for the airfoil. Okay, just check again the data, check again if it was for two-dimensional geometry, and send me the picture just to take a look. It's interesting. Unfortunately, we cannot meet in Gamma, right? Because usually we solve this on our practical classes, but we can solve it online. For example, tomorrow, we can see the project tomorrow. We can discuss the project tomorrow and try to figure where is the problem, or inside the original experimental data or in the simulation.
Okay. Yeah, so I can get everything prepared on the simulation again and get the article open, and tomorrow we can.
I also suggest to share with me these files, because I can take a look in advance and to try to see the problem, because sometimes it takes long to understand. So if you need my help, please try to share also the simulation with me before the class, so I could prepare.
All right.
Okay, people, do you have more questions for today?
Professor, só mais uma, mas acho que é mais pelo... ali na sua tela de results, acho que não, mais embaixo, quando ele dá para a gente calcular o forces, sabe? Deixa eu achar aqui. É reports, aí a gente coloca em forces, né? E eu coloquei para calcular o CL. Aí ele até plota aqui, ele print, eu ponho para print, né? Aí só que o CL dá um valor muito alto. Tipo assim, eu não entendi esse valor de CL. Porque a gente não tem a área da... Não, eu lembro que você explicou, você realmente tinha explicado isso.
In the reference values,
mas aí eu fui...
We have the reference values. Just a moment, I will see where they put this reference.
Mais embaixo ainda.
I don't see.
Na parte, deixa eu abrir.
They always put.
Na parte de na parte de reports, que aí tem um forces, que ele
Yeah, I know, but I'm looking for the reference. Here, reference values. They changed the icon, so it's hard to understand.
Certo.
And here you put the properties. To calculate aerodynamic coefficients, you put the area. The area is equal to chord because we are simulating the airfoil of 1 meter, right, in the third dimension. The density is the density on the ground. The depth is the third dimension size. The length is the chord size. The temperature of ambient temperature. The velocity, infinite velocity, viscosity is the molecular viscosity and specific heat. adiabatic.
Faz mais sentido agora.
Okay,
Agora faz
so
mais
when
sentido.
you
Porque
put
eu
all
fiquei-
these reference values, it takes automatically and calculates the aerodynamic
em
coefficient.
relação a isso.
Yeah, don't forget to set up correctly the reference values.
Uhum.
Okay.
Não, perfeito. Não, era isso. E agora ficou bem claro mesmo.
Ok.
Porque eu fiquei. De onde vem esse valor, né? Mas agora que você mostrou isso, agora faz sentido. Né?
Okay, nice.
Obrigado.
So people, thank you for participation today, and we meet tomorrow if needed. And have a nice evening. See you then.